is changing with what? With angle, with theta, and J is also changing with what? Velocity is changing with what? With the angular position. Okay. I realize that this might not be good enough because you come or might think about Eugene. This R is over what? dt. It's not over what? d theta. I can understand that. So the next graph I plot on the right hand side, okay, or I calculated, okay, using very basic formula. What you see over here on the right column is I as a function of what? Time. Position of P as a function of time. And you can see the same waveform in terms of time. Okay, so I and J of the position P, and then you can see on the right column, you can see in terms of time and velocity likewise. Are we clear? Okay, so I like this. Okay, don't just let me skim through the notes. Okay, anything you don't understand, let's say Eugene, it should be 0 or not 0. I'll take time and figure out. Is this clear now? Are we clear? Why dr over dt is not equal to what? 0. In scalar form, it's equal. Why did we do it in scalar form? Anyone? In scalar form, it's easy to say what? Hey, do you all know, right? The particle is moving at 6 meters per second. That's easy to say, yes or no? But in vector form, how are you going to describe this? In vector form, how are you going to say? Okay, in vector form, what you see is you're going to, the velocity is going to be a sine wave, and the maximum amplitude is 6 meters per second. You and me understand, but someone in the arts department have not a clue. Are we clear? So that's why we use scalar form and we use vector form. Questions? Anyone about this? Are we good? Good. Right. Or not, I feel that I don't deserve my pay. Sorry, is the weirdness that I'm getting. Right. So the next one, okay, so now this is clear. The next thing that we are going to look at, which will not be tested in term test 2, will not be tested in term test 1, is we are going to go into the absolute motion analysis. So when a body is subjected to general motion, right? When subjected to general motion, it undergoes both simultaneous translation and rotation. Okay. So if I go to, I think it was week 4. Pardon me, okay. I'm looking for a diagram, or maybe it's in. Not there yet. I do apologize. I'm looking for a diagram, okay? So just ignore me now. Or is it on week 3? So if you look at this diagram over here, I'm just going to copy the whole diagram. Okay. So is this diagram we spoke about, that we are talking about, is going through both what? Undergo both simultaneous translation and what? Motion and rotation. Okay. Now to analyze this, we have to be more cautious, okay, because we have to combine two ways of analysis. So the motion, okay, can be specified by knowing both the angular rotation of a line, okay, fixed in the body, okay, and the motion or linear motion of a point on a body. Okay, so we basically have to use, okay, we have to use a rectilinear position coordinate S. Okay, so the coordinate is in S to locate the point along its path, okay, and angular position coordinate theta to specify the orientation of the line. Okay. So we are going to apply two sets of equation. First, V is equal to ds over dt, okay, and acceleration is equal to dv over dt. Okay, so this is for the linear motion. And we are going to apply that omega is equal to d theta over dt. And alpha is equal to d omega over dt. Okay, so this is for the angular motion. Okay. So I'm going to write to you, rather than write to you, let's jump into an example. Okay, let's look at an example. You can find this example in your Avenue to Learn. Okay, can you check, is it available at Avenue to Learn? If it's not, I'll post it again. Is it there? Yes. Thank you. Okay. Let's look at this structure over here. Okay. Now, a lot of time this has to deal with math. Okay, we're going to do a lot of differentiation. Okay, let's look at this. So the bar DC, right, rotates uniformly about the shaft at D with a constant angular velocity omega. Determine the velocity and acceleration of the bar AB which is confined by the guide to move vertically. Okay. Now looking at when the first time I look at the diagram like this, it can be kind of overwhelming. Okay. So my suggestion, how to approach a problem like this. Okay. So if you look at this, what we are trying to find is we're trying to find, okay, our A velocity of what? AB. And we want to find the acceleration of AB. So these are both unknown. Okay. However, what affects AB is what is going on at point C, right? And point C and point D and point C, we know that it's linked by a what? By a arm, by a arm, and DC is known as our rigid body. Putting down a coordinate system, okay, that is our X and Y rotation about Z. Okay. So we are going to focus on this point over here. And this point is our point D. Now, point D and point C are linked. Okay. And this is our what? Our point C. Right? And this over here, right, is our what? It's our rigid body. Given to us, what is known over here, this is our what? L. Okay. So now L over here is a constant. Okay. And from here, we know, even in the diagram, this is our theta. So the next thing that we want to find out, what is y. Okay, what is y? So we know, like, y is equal to what? L sine what? Theta. Okay. So the next thing that we do a what? Time derivative. Where we state dy over dt is equal to d over dt, okay, L sine theta. So from here, we know that theta, okay, what can we say about theta? Right, theta, when omega rotate, okay, so this will rotate, this whole thing will rotate with what? With omega. Okay. And when omega, or when theta rotate at the omega radians per second, we know theta is a what? Is a time dependent. Okay. The value of theta is not constant. Whereas for here, L is a what? L is a constant. So L is a constant. So what we do over here, so L is constant. Okay, sine you differentiate is cos theta. And now this becomes d theta over dt. Then note that d theta over dt is also equal to what?